Hey everyone, I'm Gary. I'm a software engineer at Electric Capital, and today I'm going to be talking about the power of code search and how you can use it to audit contracts today. Crypto is on its way to becoming the largest open source ecosystem in the world, but with that comes with a lot of challenges and complexities for developers and security researchers. So what do I mean by this? I'm going to go over some metrics from the Ethereum ecosystem that highlight the scope of this problem. So the number of smart contracts being deployed to the Ethereum blockchain that are verified is increasing rapidly. Since 2020, that number has grown 5x. If you look at the sheer lines of code that all of those contracts consist of, it's about 290 million lines of code, which is a lot larger than many software stacks. And also butts up against some other larger stacks and organizations around the world. And if you take a microscope to look at what transactions are actually doing, you can see that they're doing a lot more than they used to. So if we look at how many contract calls the average transaction is making, it's doing 3.3 times more than it did in 2017. And so this kind of tells us that the activities actually happening on chain are becoming more complex. And there's more composability as well. And if you look at the usage of storage in transactions, the average transaction is using about 4.1 times more storage reads and writes than it did in 2017. So we kind of have these three problems where the amount of code is growing exponentially, both in the number of contracts and in the lines of code. And also what these contracts are doing is also becoming more complicated and more complex. And so to help tackle these problems, we decided to build code search for Ethereum as a public good. And the app is called Codesaw. And so I'm going to go over some use cases that you as a security researcher can use Codeslaw for today to audit some contracts. So the first use case I want to go over is finding some pesky reentrancy attacks, typically found in forks of popular lending markets. And so this example here is Compound V2. There was a version of it which had a reentrancy bug in it. And thankfully, Compound team patched it and was never exploited. But there's a bunch of protocols that forked this code, and they didn't address the bug. And so you kind of end up with this reentrancy vulnerability. And it's specifically, you can find it with the function signature do transfer out. And so if we search that on Codeslaw, we get back a bunch of contracts, about like 300. And from there, you can kind of poke through them and see if any of those are susceptible to the reentrancy attack. So on the right-hand side is that if you click into the line, you'll be taken straight to where it exists in the contract. And then another reentrancy exploit you can search for is the read-only reentrancy. This one's like somewhat new. It's been exploited a few times this year, but essentially it comes from view functions that are unguarded. And typically view functions aren't guarded because they don't modify state, but you kind of get this side effect where if you have protocol A and it has a view function that's unguarded, and you have protocol B which depends on that view function, there's a case where the contract state can be manipulated and then the view function returns inconsistent values. And so that's specifically the case here with this function get virtual price, which is part of Curve. And this function is intended to return like an oracle price for Curve LP tokens. But it's not guarded, and so if you're depending on it, you're possibly susceptible to read-only reentrancy attack. And if we search for invocations of this function, it kind of tells us what contracts are depending on it, and we get back about 800 results. So there's a lot out there in the wild. And then the next one that I want to go over is finding improper implementations of Merkle proofs. And so the rule of thumb is to use reference implementations of data structures and algorithms. But sometimes developers choose to or have to roll their own implementation of these things. And so this is a common use case for Codesaw where you want to go verify these data structures that are very important and critical to the functioning of a protocol have been actually done properly. So you can search things like Merkle proof. You can search for like Merkle verify, Merkle tree, or anything that makes sense. And it extends also to like any other data structure and algorithm, like red-black trees and so on. And then you get back a bunch of results. But for this one, I think most people are using things like OpenZeppelin, but there is definitely instances where folks are rolling their own implementations. And then the last use case I want to go over is this one actually is interesting because it came out a couple days ago. Essentially, a security researcher by the name of Zach Obrant published an audit in which he found that the PRB math library in Solidity had a bug in it, and it was patched. But essentially on Codesaw, what you can do is you can go and figure out what other contracts and protocols are vulnerable to this and have imported and deployed that buggy library. And so specifically, like there's this if statement here, and in the buggy version, it appears twice. So some of these results, you get 2 matches for it, and it tells you that these contracts have been deployed with that buggy library. And this is pretty cool because there's not really a package manager that tells you all the versions of imports and stuff. So one use case of Codesaw is to sort of fill in that gap, and you're able to kind of dig into the supply chain if you're clever with the contracts and digging into the actual contents and creating these sort of diffs. And so after you find your contracts of interest, we also have some features on there which help you dig into the information about it. And so this one right here is a chart showing the call dependencies of a contract. And so a lot of protocols are multi-contract, and user typically interacts with like one contract, but how it works, like how it works, the contracts make a bunch of different calls to each other, and so you get this like value flow and execution flow, which isn't immediately obvious if you're looking just at like transactions. And so we created this sand key chart of the call dependencies, and so it's constructed by summing the gas spent between in and outbound calls. And so that's the representation. The weight is represented by the thickness. And then another thing you can look at is proxy diffs. So this chart highlights the amount of upgrades amongst the top proxies in Ethereum. And so you kind of get this like upward trend, but essentially, proxies and upgradable proxies are probably here to stay. And so on Codeslaw, if you're viewing a proxy contract, you can view the versions of the actual logic contracts, and then if the current and previous contract versions of an upgrade are verified, you can also view a contract diff. And lastly, a little bit about the roadmap. We're kind of looking at it in two ways. One, like unearthing more of this information for devs and auditors. So that's like next is to show contract storage. There's a lot of live state, configuration state that also leads to exploits and vulnerabilities, and so that's important to surface. And then we also want to add annotations so that when you go view a contract, there's already a lot of community wisdom or even like comments left by the team, so you can quickly understand like why they did certain things in the code. And then the other thing we want to work on is contributing to the data ecosystem. So planning to add contract verifications specifically for languages that are not Solidity, since the Solidity ecosystem is pretty robust. Yeah, and lastly, we can't make Codeslaw as best as it can be without your input, so please give it a try. Let us know what features are missing or what you think could be improved. Thank you.